Record on this computer.
Now muting.
Start it before.
For
the first time, I'm not going to start it on like on the right, the right time.
Yeah.
And I think that's good. If anybody online could just write in to make sure they could hear us here, that would be great. Dan, you can. We got a thumbs up.
Yeah, I'm watching the chat and I can see everybody.
Did anyone write in that they could hear us?
No. Not that I see. I'm going to send a message out.
Oh wait, I just saw a chat come in.
Oh wait, yeah. Aaron says I can hear.
Yay! Okay.
Yeah, you can hear.
Okay. And it's noon. Okay.
Wait, yeah, I thought you were going to.
So good afternoon, everybody. This is Jen Mixes Olds, and I'll be introducing our speaker today. Thank you all for tuning in to, this is the final fall environmental acoustics seminar. And our speaker today is going to be Dr. Jennifer Dijkstra from the School of Marine Science and Ocean Engineering, and also the Center for Coastal and Ocean Mapping. Before I turn it over to her, just some housekeeping. I want to let everybody know that we will have a spring series, and that will be sent out in advertisements in January. We likely will have a January, February, March, April speaker. We will have a regional symposium again that was just finalized with funding from the Acoustic Society of America after the meeting last week. And it will be here at the University of New Hampshire, most likely at the end of April. As soon as we solidify a date with catering and find an appropriate room here at UNH, we'll send out that date also, and that will be run with a very similar format where we'll have two keynotes, one in the morning, one in the afternoon, fill up the morning with speakers. We'll have a full-blown poster session, students, faculty, associates, business, industry, whoever would like to participate will be welcome to participate. So those are the only housekeeping things I can think of. Unless one of you or Dan have anything? No? All right, well then it is my privilege and honor to introduce Dr. Jennifer Dijkstra. She sits 3 doors down from me, and it's great because here in the Center for Coastal and Ocean Mapping, there aren't a whole lot of biologists. It's really nice to be able to bounce things off a fellow biologist, and I'm let her talk about how she's using acoustics to understand Gulf of Maine ecosystems.
Okay, so thanks, and let me know, or Dan know, if you can't hear me. I just want to thank Dan and Jen for inviting me to give a talk to this environmental group. I will be totally and perfectly honest and say that I am not an acoustician. I'm not even a bioacoustician. I am a marine ecologist. But luckily, as Jen says, I'm 3 doors down from her. There's a lot of acousticians here in the center that I collaborate with, and so it's been very fruitful collaborations. So, having said that I'm a marine ecologist, the focus of my research is on habitat forming species, but primarily changes in ecosystems and changes in habitat that occupy those ecosystems. And for those of you who don't know, habitat forming species, or otherwise known as foundation species, are 3-dimensional. And they can be things like coral in the deep sea that you see here, or sponges. They are here soft coral and shallow coral reefs, or macroalgae or eelgrass. And so these foundational species provide habitat for other species. So they essentially enhance biodiversity within an area. And so these foundation species also perform other ecosystem services. They can sequester nutrients, for example, nitrogen. They also here within eelgrass beds, they have root systems, and so they're found primarily on muddy or sandy shores, and sediment is trapped within those root systems, and so they can help prevent erosion. They attenuate currents and waves, and so they can trap suspended sediments and particles. They're also, they can also store carbon, and this is a hot topic now for, with eelgrass, where there's a lot of research on blue carbon storage. As I mentioned, they're important habitat for fishery species such as lobsters and flounder, as well as for very small mesoinvertebrate species that that occupy single individuals and that use them as habitat. And as I mentioned, they enhance biodiversity. And one of the questions that I'm really interested in is how they can, how changes in these foundational habitats can affect food webs. And so, as we all have probably heard, or hopefully have heard by now, globally we're losing our foundational species, and these foundational habitats are changing and shifting. And that's also occurring in the Gulf of Maine. And so here, this is a graph. On the x-axis is year, and on the y-axis is metric tons of eelgrass biomass in Great Bay. And what you see is about a 60% decline in eelgrass biomass in the bay. And a lot of times the eelgrass is being replaced by macroalgae. This is just an example on the right-hand side of a Gracilaria species that is becoming quite common in our area. And these shifts are, foundational shifts are reflected in the marine environment, where we see, where we used to have a dominance of kelp beds, and in the late 70s and 80s, and this has shifted more towards turf-dominated communities. And one of our long-term studies are really based on diverse surveys where we have quadrats, very small quadrats, about 1/4 square meter or 1 square meter, and we're assessing percent cover in those quadrats. And also, because they're diverse surveys, we're also surveying a very small area. So we have, so one of the things that we are really interested in knowing, and which certainly here at the Center for Coastal and Ocean Mapping can help with, is how do these small surveys translate to larger scale areas? So essentially do our small surveys, are they representative of larger areas? Okay, so today I'm going to talk about 3 studies. One is developing and field validating new methods to detect eelgrass and measure canopy heights for mapping eelgrass. A second study is transferring the methods that were developed for eelgrass mapping to mapping kelp and non-kelp habitats in the Gulf of Maine. And then a third study, which is really a pilot study, and I'll only talk about briefly, and that's because I know most of you are bioacousticians, is to use soundscapes to understand ecosystem change in the Gulf of Maine. Okay, so eelgrass, so acoustics and seagrass is an intensely studied topic, and more so for the purpose of removal of seagrass from acoustic data. Because eelgrass have gas-filled pockets within their blades and they have a higher acoustic impedance than the surrounding water, which makes them effective in reflecting and scattering sound. For the equipment that we used a multi-beam transducer with an internal motion sensor. it was mounted to a pole that was then mounted to the small vessel, and we used a frequency of 200 kilohertz. Our study area was Great Bay and Little Harbor and Portsmouth Harbor. And I should say, I'm saying our, but this study was really done by Ashley Norton. This is part of a chapter in her dissertation, and Dijkstra. And so these studies were done in Great Bay, Little Harbor, and Portsmouth Harbor. These are environmentally distinct areas. So Little Harbor is very turbid, so is Great Bay. Portsmouth Harbor is less turbid, and the eelgrass there is quite a bit taller. I should also mention that in Great Bay, the eelgrass has been intensely studied for a long time. And here we see, this is a depiction of depth. Essentially, this is a depiction of what the data looks like from the water column over the eelgrass bed, where you have depth below the transducer on the x-axis, and then on the y-axis, and then on the x-axis you have a cross-sectional distance from nadir. And what you see here is the eelgrass, which is the intense red, the seafloor, which is that dotted black line, and the side lobe interference. And what we're primarily interested in is understanding the canopy height and of the eelgrass. And the reason for that is because the canopy height ecologically is really important for species and for the habitat in and of itself. So, for example, a higher canopy height can support greater biodiversity, and number of individuals. And so here, this is an animation of a line of data from a patchy area of long eelgrass. And the green points are the canopy detection, whereas the black points are the seafloor. And for the canopy returns, Sam and Ashley only considered within 20 degrees of nadir because of the effects of side lobe interference further out in the swath.
Okay.
And here this is essentially
I don't think this is worth watching.
eelgrass along a sonar track. And again, you have and then ping number on the x-axis. And the black line indicates the blue line indicates the height of the canopy. And what's interesting about this profile, and I should also say that this is a profile from the nadir beam, so it's essentially a single, you can think of it as a single beam echogram. But what's interesting about the profile is you can see the patchiness within the eelgrass, and you can see the canopy height of the eelgrass. And this is really very important because of, again, if you have a patchy eelgrass, that indicates that that eelgrass bed isn't as healthy, it's more continuous. And here, so to create a map of eelgrass beds, we created a 2 digital terrain model, and one of the seafloor, which is that gray area, and the other is of the eelgrass canopy heights, which is the colored area. And so it's from 0 to 3 meters. All right, so one of the results of their findings, which I found to be really interesting, was that you could see within the acoustic data, so the blue and the green are the acoustic data, and that's overlaid on imagery. And the blue indicates absence of eelgrass, whereas the green indicates presence of eelgrass. And so what was of interest to me was you can see a level of detail of patchiness within the eelgrass beds. And so you can see that in the along track direction of the acoustic data, as well as in the cross track direction. And another result that they found, which I found to be of real interest, is this comparison between eelgrass identified in imagery versus eelgrass identified in acoustic data. And so here is an image in which eelgrass was identified, and this is in green, kind of light green, and then overlaid on top of that is the acoustic data. And so what's quite interesting about this is that, again, you can see the patchiness within the acoustic data, whereas you don't see that within the imagery that was within the imagery data. So essentially, somebody has just drawn polygons around what they feel is an eelgrass bed. And I should also mention that the imagery data, as well as the acoustic data, was collected in the same year at the same time. The other part I'd like to mention, and again, this is of interest, is that as you go south, and you can see this arrow with 390 meters next to it, there's eelgrass is delineated within the imagery data, but it wasn't found in the acoustic data. And this really suggests to me that this is a misclassification where in this area, it's probably not eelgrass that is observed in the imagery, but more likely macroalgae. And so the conclusions of the study, we can detect canopy heights, which is great. We see a level of patchiness of eelgrass within the acoustic data, so it provides a much greater level of detail within the data, much more so than a lot of other remote sensing tools. It appears to be certainly a better tool for accurate assessment of eelgrass beds than of imagery. And again, this is primarily because ecologically, if you have a patchy seabed and if the canopy heights of the seabed are of the eelgrass is low, then you don't have as healthy of ecosystem. Okay, our second study was to transfer the methods that were found to work for the eelgrass beds to macroalgal communities. And here, we wanted to really see whether we could first identify kelp based on their canopy height, and then differentiate kelp from non-kelp habitats in the Gulf of Maine. And this is because our long-term studies indicate that kelp is declining. But again, our long-term studies are based on these quadrat surveys. And so just, let's see. So just for everybody's, I guess, information. So the left picture is that of a kelp bed. The middle one is that of turf macroalgae, which is what we primarily observe here. And then on the right-hand side is sort of a mixed community. And so, unlike eelgrass and other kelp species, the dominant kelp here in the Gulf of Maine, which is the sugar kelp, Saccharina lactissima, does not have these gas-filled pockets. And so its acoustic return its acoustic signal doesn't scatter as much or as intensely as that of eelgrass or of other types of macroalgae. But what is great is that the kelp is taller than that of the neighboring species. And so we can now use canopy height to then distinguish among kelp and hopefully among kelp and turf or non-kelp habitat. So we did a pilot study, and this was at Nubble Lighthouse in Cape Nettic, Maine. And so Here, this is one of our long-term subtitle study sites. We use the same mounting system and the same sonar, as well as the same frequency, which is 200 kilohertz or hertz we used for the eelgrass mapping. And here, so we mapped Cape Nettic, and then we ground truth. And here, our ground truth consisted of collecting a large number of 1 square meter quadrats in which we had a team of divers, and we placed a quadrat on the seafloor. We photographed the quadrat. We then collected canopy heights of 3 to 5 individual seaweeds within the quadrat. So we had then had and this included the tallest seaweed within that quadrat, and then we averaged it to create an average canopy height for that quadrat. We also georeference each quadrat by having a diver at the surface with a Nikon Cool camera, which has an internal GPS in it. And our dive team was connected by a taut line. And so whenever a photo of the seafloor was taken, then the diver at the surface would take a photo. And so these canopy heights were then overlaid on the ground truth data, and average canopy height for each quadrat was then correlated to the corresponding canopy height for that point. And these are our results, where our acoustic canopy heights, which are on the y-axis, and our ground truth canopy heights, which are on the x-axis. We had significant correlation and pretty good correlation. There's variation in every study, and so if you have a perfect correlation, I always kind of question that. So I'm sort of happy we don't have perfect correlations. And then we classified the acoustic data into kelp and non-kelp canopy heights using the data thresholds of 0.3 meters to about 1.5 meters. And we use this canopy height because our in situ kelp canopy heights ranged from 0.3 to about 1.5 meters. And we then compared that, or performed really an habitat classification accuracy assessment using our photo quadrat data, and we found that there was an 86% overall accuracy, which is pretty high. So we were very happy with this. But that's one site, and we wanted to know, will this occur at all of our sites, or is this just sort of a one-time only result? And so we subsequently surveyed several sites, several shoals, and again, these are sites in which we're very familiar with. We dive at all the time. We know the species.
Go to webinar. Thank you.
And
Thank
so
you.
at these sites, we collected underwater video footage of about a 10 by 10 square meter area. And then we stitched the footage together to create a photo mosaic of 100 square meters. And within each photo mosaic, we identified to the lowest taxonomic denominator as possible the individual algae. We also assessed percent cover. And then we compared that percent cover to the percent cover that we found using the acoustic data. And this is using the height measurements of 0.3 to about 1.5, which indicates kelp. Below 0.3 indicates non-kelp habitat. And so what we found, and so on the top graph is percent cover, the bottom of diver mosaics, the bottom graph is percent cover found within the acoustic data. And so what I want to point out first is that you can see similar patterns of, and so you can see that non-kelp habitat habitats dominate at all sites, and this is found for both the diver and the acoustic survey. What was real interest to me was that the acoustic survey also found higher abundance of kelp than we found in our diver surveys. And to me, this is something that I feel is real, because our diver surveys are at such a small area. And so what this suggests to me is that by sampling a larger area, then we might capture more of the kelp that's in that system. And this could be a very useful tool for long-term monitoring or for even experimental studies that will affect community dynamics. And so our conclusion was that we can detect kelp beds, certainly within 20 degrees of vertical incidence, and that we can use that then to delineate between kelp and non-kelp habitat. Okay, so we're going to switch gears a little bit and talk about using soundscapes to understand ecosystem change in the Gulf of Maine. This is a study that myself and Dylan Wilford, one of Jenn Mixes-Old's master's students, Jenn and I did last year. And this is a pilot study, a very, very pilot study, where the goal was to see whether we could hear different sounds within different habitats. This study was conducted in winter because that was an opportunity for us to use the hydrophones that were available. And though it was really, really, really cold, it was, are you sure, man? I don't know. It was a little chilly. But what was actually quite nice about this is that winter is a time of the year when there's very little going on in the Gulf, and so animals are fairly inactive. Some animals are dormant. Some animals have migrated to deeper waters or to the south, and so animals like sand dollars or their predators, crabs, are still fairly active. And so we placed a sonar system. Again, this is at the Isles of Shoals, which is a cluster of islands 7 miles offshore. We placed, sorry, not a sonar system, a hydrophone in a sandy environment in a cove that was dominated by sand dollars. And then we placed another hydrophone in a rocky environment dominated by seaweeds. And so here, this is a power spectral density profile. And here, what you see here is, so the power spectral density is on the y-axis and frequency is on the x-axis. I'm really just starting to learn about these graphs, so bear with me. And so all I really want to point out is that at this sandy site that's dominated by sand dollars and by their predatory crabs, we see greater variation in the sound as opposed to that of the site that's dominated by macroalgae. And so the top graph, power spectral density profile, is that of the sandy environment, and the bottom graph is the macroalgal habitat. And so it could be that the differences in the variation of sound, particularly at that higher frequency, may be due to the sound created by sand dollars munching on the microalgae that's in the sediment. And it could, but I think further research is really needed to determine that. And I think that is it. So I just want to thank my funders and all my collaborators for their support and for helping helping to teach a marine ecologist acoustics.
Okay. So do you want to MC questions, Dan, since you've got it?
Send out a request.
All right. And I'll say,
I'll
as people are writing in questions, I want to remind you, if you're viewing with more than one person, please let us know so we can kind of keep track. We've got 15 here in this room already, and I know I saw 32 logged in, and I know there's more than one per person. So I just want to say thank you, because this was a really nice demonstration of how an applied acoustics methodology can be used with traditional methodologies to see, what we can learn in addition to those traditional ways, or what we were missing. And so I have a particular graduate student who's trying to think about acoustics and genomics. So I think that there's a lot of similarities between what you've just seen with a traditional method compared to acoustics, and what we're missing or what we're gaining. And so I just wanted to say thank you, because that was particularly of interest to me, and how you did that. And Dan, I'll turn it over to you for questions.
So I don't have any questions yet.
We have questions in the room.
Oh
here,
yeah,
though.
so maybe Tony, do you have one? Then we'll jump
I have
in.
two.
Maybe just one.
Okay.
So I know that this was Ashley's work.
Yeah.
The first part.
Yeah.
You showed a plot of biomass over the past 2 decades.
For
and
eelgrass,
from
yeah.
1,600 metric tons to 400 or something
Yeah.
like that. How were those measurements made?
Those measurements are made by, so what you do is you have a quadride on the seafloor, and then you're collecting all of the eelgrass within that, and then measuring, and then bringing it to shore and measuring the biomass.
Okay, so the real question is this patchiness that you observed with the acoustics, is that going to change? You're going to have some sort of step function because it's a different method. So if you try to put a dot on that plot, do you have any idea of where you're going to shift up or down?
In terms of biomass?
Yeah.
So there's not a direct correlation between what is observed in acoustic data and biomass of eelgrass. And so what the acoustic data currently shows, or you can currently detect from it, is basic metrics like patchiness, canopy height, and even canopy height. It's really the in situ canopy height. It's not traditionally with eelgrass, people measure canopy height from the roots all the way to the edge of the blade. And with the acoustic data, you're not observing that. You're observing the canopy height as it is in the water, and whether that's laying over or whether that's upright. So that's what you're observing. And so, but even still, you within a site and within a region, if it's the same species, you can then compare canopy, even in situ canopy heights within that area, to say something about the health of your ecosystem. Yeah.
First study as well. So you showed a map that was polygon from aerial photography.
Yeah, they were collected in 2015.
Yep, and then on top of that you have the sonar data. And one of the things that you pointed out was that
Should I go back to the image?
the polygons cover a larger extent, and they don't drop like the patchiness
They don't.
out. But my question is, that patchiness benefit of the eelgrass ecosystems that they provide, does the patchiness that's not accounted for actually make a difference in the extent of the ecosystem service?
Yeah, so
repeat the question just so people can hear.
Please.
So Annie was just asking about this slide where we have the sonar data overlaid on the imagery data, and where the imagery data is drawn as a polygon, and where the sonar data is the patching of the eelgrass. And she was asking whether the patching of the eelgrass made a difference in terms of the ecosystem services that the eelgrass provides. And the answer is yes. So if you have a highly patchy eelgrass system, then you are then that provides certainly less that provides less habitat for species. And so you have less biodiversity. Also in terms of the amount of sediment that traps or kind of binds together. So you have less, so there's more erosion as well. And so, and also if you have a highly patchy eelgrass bed, then that could indicate that the water quality declined to support a smaller bed. Absolutely. So it's actually really important for restoration, for coastal. Yeah.
Like, this is a pretty large
Quantify.
area, so if you have large differences, if you're looking at a smaller area and you're only missing some of the patches, that's gonna make it
That would depend on that would depend on kind of the scale at which you're looking at, exactly as you said. So it depends like how small is or how large is. Yeah.
So we have a couple other questions here. Aaron asked, I'm not sure where Aaron's from, but is acoustic measurement done by bouncing sound off the seafloor? And then again, how were the measurements taken? This was Aaron's question.
So it would be done. So the measurements were taken from the acoustic signal, and so one ping is bouncing off the seafloor, and a second ping is bouncing off the eelgrass. No, that's not correct.
Can you show the?
put the sonar image back up.
There.
Sorry, it's a single ping. You're right. You're right, but you have two peaks within that single ping, and one peak indicates the seafloor, and the second peak indicates the canopy height of.
And we had another question from Brown that they asked, is it too noisy for summer acoustic recording to be taken and useful?
Noisy as in you mean for passive acoustics or for active?
I'm wondering if they mean
acoustics?
because of the maybe increase in bioacoustic conditions in the summer. Is it a little bit, I guess there's a difference. Maybe.
There's definitely more boats. Actually, I would be really interested to see whether. So I think once you can filter out the noise of the boats, then you would just be looking at the habitat. And I would be really keen on knowing whether kelp habitat certainly has greater noise or soundscapes than other habitats. That would indicate that they might support a higher biodiversity or abundance.
I would say too that because this is shallow water, low frequencies will travel further than high frequencies. So if you look at just the high frequency component of the spectrum, you may be able to capture the local biologic component as opposed to the lower frequencies.
Just the anthropogenic noise. So that was the follow-up question. What about, would you expect there to be more biophony or more biotic in the summer that might make the evaluation of the data a little more complex?
Biotic contributions?
The animals that would be producing.
Yeah, you would definitely expect to have more sound in summer than in winter. Yeah, absolutely.
And then I had a question too. You would come back to your other question. So talk about how sand dollars make sound.
How sand
How
dollars?
is sand dollars making sound?
So sand dollars move across the sediment, and they're just like sea urchins. So the sea urchins are consuming macroalgae, but sand dollars are filtering out the microalgae from the sand. And so as they're filtering out the microalgae, they're making noise.
They're making some sort of sound. Can you make sound? What does it sound like? I have no idea what it sounds like.
There is no way I can make that sound. That's,
As a terrestrial biologist, I'm curious what a sand dollar
That's cool.
it is. It's, yeah.
Grind some rocks together, Dan.
That's it? Okay.
That could be a really good experiment, though. Just put sand dollars in it. Actually,
Tony, you got a follow-up in bed, maybe?
Yeah, so your soundscape plot, the two soundscapes, is that right? I
Yeah.
couldn't read the axes. So
I know yeah, sorry.
I did that on purpose.
I did, I totally did. I went through it pretty quickly.
Frequency
So-
axes.
The frequency is from 10 naught to 10.4. And fourth.
So there's a peak.
10 kilohertz. up to
10 kilohertz, yeah.
So there's a peak between about 2 kilohertz and all the way from about 2 kilohertz to 10 kilohertz. But that's the region where breaking waves.
You mean right here?
Yeah.
Okay,
Well, all of that.
all of that,
From like 2 kilohertz all the way.
yeah.
That's the reason we're pulls from breaking waves. That's exactly where they're going. So you might have two different hydrodynamic conditions at the two sites, which you need to disentangle from your biotic contribution.
Okay. Yeah, no, that's a really good point. I would have expected to see that at Star Island too, because they're also, the hydrophones were deployed at similar depths and similar distances away from the shore. And so I would have seen, I would have expected, but maybe there's differences, certainly maybe at that point in time there are differences in wind and currents or
Way
waves.
off in the shore, which side of the
Yeah,
island
yeah,
you're on,
yeah.
how small the island
That's a
is,
really,
The wind
yeah,
direction.
wind direction.
yeah.
So there are different regions where different things will
Influence that.
voice, including the non.
And the big baleen whales between 20 and 30 hertz in the bottom.
Yeah.
You're catching
Yeah.
some
Yeah, I
baleen
didn't
whale
mention
signal.
that. Yeah.
There they are.
Yeah. You thought that was a fin back.
Yeah,
Right,
fin. It's kind of blue.
Let's see. Can acoustic measurements identify different species of kelp or seaweed? Does it just show general growth? Species level.
You can't get species level with using acoustic. Well, maybe with more in-depth measurements, you might be able to, but not with how we were measuring it.
You only had a
So-
single frequency.
We only had a single frequency.
I
so
imagine
if you
with
use
a
multiple-
broadband
Yeah,
acoustic,
yeah,
active acoustic system,
yeah.
you might be able to tease out
Yep.
some,
Yeah.
because if the gas bubbles are bigger or non-existent or oriented differently
It's
in the different
really-
species, I bet you
yeah.
a broadband system would be super
So
cool.
it would have to be a different
You
reflector.
could.
Yeah,
Yeah,
yeah, that's what I'm saying, but a broadband
Yeah,
would definitely
yeah,
be able to
that's-
capture
yeah.
that a little bit more than a single frequency.
Yeah.
That's cool, let's do that.
That would be great.
You add
Yeah.
that on top
Yeah.
of your
I
photos,
think,
actually, call it
though-
hyperspectral.
Yeah,
That's
almost
it, yeah,
almost like a
exactly.
lighter.
There's a
Yeah.
sexy
But I
picture
think-
for you.
Yeah. It also depends on the time of year. So the amount of bubbles that an algae produces is really dependent on time of year, on amount of sunlight reaching the seafloor, on temperature. And so it's going to vary quite a bit,
I
right?
think you need more funding to study.
I know,
This is
it would
kinda
be
cool.
great.
Do
It
you
would
have another
be really
question?
cool.
No, I know, but Ben had one more.
Mostly, I was just sort of curious about what the sort of tidal effects on height, tidal and current effects on height when you're doing the canopy height measurements would look like.
For the eelgrass?
For the eelgrass, for really for all of it, right? Because if you get a strong current, that's going to lay everything
Yeah,
down.
exactly.
Mm.
Yeah.
So,
Yeah.
It's still not going to look like turf, I'm sure. But did you manage to get a chance to test for that at all?
No, we didn't look at currents. So Ashley, however, did look at currents with eelgrass, and she found that that currents make a big difference in terms of kind of the positioning of eelgrass. But eelgrass is a little different because it has those gas-filled pockets, and those gas-filled pockets will keep the blades upright in the water. Not upright, but they'll keep them above the bottom. Whereas in our native kelp, this sugar kelp, it doesn't do that because they don't have those gas-filled pockets. And so, I mean, when I'm diving, certainly you've seen it as well, when you dive, kelp is traditionally laying over on its side and it's not upright in the water column.
I don't have any other questions
I was
from
gonna
the
say,
audience.
she's been grilled for 15
She
minutes.
has.
So we should probably give her a
It's
break.
good, it's good.
And thank you.
Thank you.
For everybody logged on, stay tuned. Watch your email for the spring seminar lineup. All right. Thank you so much. Everybody have a good holiday.
I have another conclusion for you.
Oh, it's good.
Let me stop this.
So if you leave 30 minutes for questions, you'll get